fine. Let's get started. We will continue the cogeometry. So I just enhanced the lecture note. So if you want to read the lecture note, please look at the updated file.
Did you start recording?
Oh, thank you very much. Yeah, I start. Yeah. Somehow the last time problem is the first half I didn't record, and the last half somehow connection here is not good, so it was whole black. I'm sorry about that. Okay, last time we start talking about color geometry, and some people asked the question about how do you extend the R. I mean, R equal to 0. There is some how to say, so the ellipsoid, so this is R is constant, and at that some R equal to 0, you have the surface, and then at the boundary of, so like a disk, it becomes a disk. At the disk, at the boundary, you see the ring singularity. So that's and then some people ask, well, how can we extend the region of R goes to negative direction? And in that case, I just add a bit more explanation about how to extend the kind of like I just introduced so-called classical coordinate for Kerr geometry. The trick is that the Sine equal to 0 is the, again, as I failed to explain last time, but this is the plane or TR plane. Also, if you want to include phi, is also okay. Is the totally geodesic. And then furthermore, what's important is that the metric at this point will become the following thing. So the metric become more like a car. Not car, Reisner stone. That's delta sigma 0 dt square 0 sigma and dr square, like this way. So it becomes like this way. So total geodesic means that the geodesic on the plane stays is also geodesic in entire plane. So therefore, the causal structure. So if you look at the geodesic on this theta equal to 0 plane, it's totally fine. It doesn't violate any causal structure. So if you focus on theta equal to 0, the space-time structure is much more, how to say, transparent. And then here you can just use this coordinate is there's no mixed term like a dt dr part. It will be gone once you restrict yourself in the theta equal to 0 plane. And then furthermore, one can just write down, so this metric as the following form. So f du and dv, and where du and dv, small u and small b, where the f is equal to delta r square plus s square, which is equal to r minus r plus r minus divided by r square plus s square. And then u and the b are t plus minus r star. I mean, it's just the same thing as a repetition. I mean, of the Reisner-Nordstrom case, where the r star. I don't know. The previous case I used the lower star, but anyways, it's a very subtle thing. The r, and then which is r plus. I mean, it's just same thing as the Reisner-Nordstrom case. It is tortoise coordinate. And and then m r minus, and then square m square minus a square, and log r minus like this way. So again, you can see that here the classical how to say Kerr's coordinate, but to go to the causal structure around the here r is equal to r plus and r is equal to r minus. So you have to be a bit careful about how to define the capital U and capital V, and so on. So around the r is equal to r is equal to r plus, we can just define U plus is something like a minus plus e to the minus kappa plus u, and b plus is e to the kappa plus v, and so on. And around r is equal to r minus, u minus is equal to minus plus e to the kappa minus u, and b minus is equal to e to the kappa minus v, and I have to be careful about sign somehow. Like this way. Like this way. Now where kappa plus minus is just a derivative of f at the point, the corresponding point, sorry, kappa, r plus minus. Then the metric is something like this way. Around that point, metric is something like 2 times kappa plus minus minus 2 du plus minus dv plus minus, like this. So you can just write down the coordinate transformation and so on. So one can just write down the metric on this plane. And it turns out that the theta equal to 0 is around this point, it's really middle. It's theta equal to 0 is really middle. Theta equal to, so therefore there's no singularity on this plane, and there is no like how to say, and r equal to 0 corresponding to u minus b minus is equal to minus 1 as far as I know. B equal to minus 1. So that one can just extend this classical coordinate to the u r goes to negative region. So that there's no, if you only look at this theta equal to 0 part, and then use this classical Kerr's coordinate, I don't know how to pronounce it anyway, so one can extend the space-time region to the this region. So that's the slightly better way to explain the causal structure of this Kerr geometry. That's one thing I just wanted to add quickly. And another thing is that we encounter so-called ergosphere. Ergo is, last time I explained energy. Actually, it was correct. Energy. So in Greek, it's energy or work, it means. And then, what is the ergosphere? How to characterize the ergosphere? Do you remember? What are the characteristics of ergosphere?
GTT becomes.
Good. So GTT is in fact become the positive or equal to 0. Okay. Or negative? Oh, sorry, negative. Sorry, negative or equal to 0. I mean, the surface of ergosphere is the equal. So the equality hole holes at r equal to 0, which is m minus plus m square minus a square cos square theta. And then okay. So equality holds at this surface, but in between, and this equality holds. This equality holds at theta equal to 0 or pi. Okay. So that's the case. So okay. So therefore, if you just look at the last time as I mentioned. So here you have the r equal to z inner horizon. Sorry, my drawing is horrible. R equal to z minus inner horizon, and r equal to plus is outer horizon, and the Argos sphere is something like this way. Like this way. R equal to 0. Okay. And this part, so partial t becomes space-like. Space-like. And he asks a question: when does it what kind of the vector becomes the time-like? So the question is the time-like vector. So this will give you so-called frame dragging. Or it's a more precise way is called dragging of inertial frame. Frame of inertia? I don't remember. Inertial frame. Okay, and then let me recall a little bit. The frame dragging. So the infinity observer is the angular momentum at the measured angular momentum measured at infinity is p phi equal to 0. So this is it's called 0 angular momentum observer. Okay, so this is called 0 angular momentum observer. Somehow astronomy or whatever relativists somehow use this ZMO. Somehow it looks like a very common usage. But if you consider the angular velocity d phi or dt, this is the angular velocity instead of a momentum velocity. This can be written as the d phi, phi dot, and then t dot. Of course, dot means the derivative with respect to the what was that? Proper time, and then g phi phi, and then p phi, and then here gtt dt plus gt phi p phi, and then we know we said this is equal to 0. This is equal to 0. And then this is just the important thing is that since there is a cross term on phi and t in the metric, so this angular velocity still is non-zero, even though this momentum, angular momentum, is equal to 0. So that's the point. And then that is given by 2mRA divided by delta sine square theta. Okay, so that's the case. Okay, So therefore, even though the momentum, angular momentum measured at the infinity is zero, somehow angular velocity is non-zero. And so this effect goes to okay. So the important thing is that r goes to infinity. It behaves like a over r cubed. Or a over r cubed. So if you go to infinity, this angular velocity becomes really tiny. But if you enter the how to say ergosphere and so on, this effect becomes really important. Okay. So this effect becomes really important, and that is the one thing is called so one analysis we did is that the become tiny. Well, analysis we did is that if you consider massive particle, U is you have like how to say people write down like this way, omega phi del phi. So this is the vector, which is something like a ut 0 0 omega ut like this way. This is time component r theta phi. So then since the u dot u minus 1 is u dot u, which is ut square, and if you take inner product, the cross term up here, that's g omega g t phi plus omega square g phi phi. Okay. And then in order for this one is negative, so this has to be negative, so that will give you some constraints on the omega. And it's omega, constraints on omega, and omega has to be something like this one. Okay. And the which is the omega plus minus is equal to, did I write that? I call it this one, I call it this one is small omega. I call it this angular velocity is small omega. And omega plus minus square root omega square minus gtt g phi phi. Okay, so that's the constraint. So therefore, and if you write down this omega plus minus in a figure, it's much more illuminating. So since it's written in terms of the A or the or whatever, M or and so on, angular momentum mass, so this omega plus minus depends on the angular momentum. And for instance, A equal to M over half case. So as you can easily see, so at our surface GTT is equal to 0. Okay? Our surface how is that? Surface of our sphere GTT equals 0. So therefore this is 0. So if you take a square root, omega minus becomes 0. Okay? Always omega minus becomes 0. So the shape look like this way. Like this way. This is omega plus and omega minus, and this is r plus, no, r0. R0 and r plus. And then, yeah. Okay, so that's the case. So at the r plus, yeah. So omega r plus is indeed GTT, g phi phi, r plus. Okay. So at the outer horizon, this part will be gone. Okay, this part will be gone. This curved part will be gone because of this property. So therefore, this point is in fact equal to omega. Okay. So at the outer horizon, the omega plus and omega minus coincide because the square root inside the square root becomes 0. So That's the property. I'm not gonna do the calculation. It's whole. I mean, the car. If you do it by hand, it takes a lot of time. Just if you use Mathematica, it's super easy. But I'm not gonna do calculation. All the calculations because it's horrendous. If you do, and also most likely I will make a mistake. So I'm not gonna do that. So anyway, so the R plus that's a property, and omega minus becomes 0 at the point at the surface of the surface of the Auger sphere. Okay. So that's the case. Then note that so this diagram, Anyway, so that's the case, and the omega can be only taken like this way. Okay. So therefore, if you look at the inside of Auger sphere, so the angular velocity always be non-zero. Okay, non-zero. Moreover, so as I mentioned, non-zero, and moreover, as I mentioned, this is R0 and R plus. Anyway, R plus, and R0, and this part so in the annulus become an Auger sphere, the original Auger, and then same equal to pi over 2. As I mentioned, even though you start with the and the rotation of the angular momentum of black hole is this direction, counterclockwise particle will drag by frame dragging, and at the point of the surface, if you intersect with the surface of Auger sphere, angular momentum becomes angular velocity becomes 0. Okay, and then they just become co-rotating. Okay, like this way, co-rotating like this. So that's the counter-rotating, rotating. Objects become co-rotating, forced to be. That's because of the effect of frame dragging. Okay. So always has to be positive. So angular velocity. And then furthermore, important thing is that what's going to happen at this boundary. So inside is allowed region at the boundary. In fact, this quantity becomes 0. Okay. At the boundary R minus or R plus. If you plug into here, of course this becomes 0. Okay. So therefore, this vector become null instead of time-like at the boundary of this. So therefore, here that the boundary becomes. If you take the angular velocity like this way, this is the null vector. And the inside here is time-like. So U is time-like, U is this guy. And then but at the boundary, it becomes null. Okay. So, but that makes sense. So that because here around here, so light cone can be. I don't know how to draw. It's just schematic. Light cone become like this, but at the point here, the light cone is really, it's hard to draw. But anyway, so it become like this way. So at the horizon, so the only new vector can just stay at the horizon, at the horizon. So therefore, at this point, the vector should be null, become null. And then so here, so the new vector here is particular new vector which plays an important role in the important role in this Penrose's Penrose process and so on, and the black hole thermodynamics, and this omega is equal to omega r plus. Okay? So it become null. Null at r equal to r plus. So exactly this vector is at this point. Here I should also mention omega r plus. Okay. And then here is omega r plus is indeed given as follows. It's a very simple expression. As far as I wrote in the text here. And this is indeed equal to a over r plus a square. Okay. So that's the body of the angular velocity at this point, or the outer horizon. Fine. So that's the little bit recap of last time, and also a little bit enhanced version explanation. Any question at this moment? It's okay. I mean, fine. Repetition is father of learning. So people call it this part is the surface of our sphere is the static limit because the angular velocity vanishes. That's at this point. At this point, always omega hits 0. Capital omega hits 0. So let's move on to the geodesic motion around the Kerr black hole. For massive case, I'll be schematic. For geodesic motion, around Kerr black hole. For massive case, I'll be in schematic. Massive particle. And the massive particle, I mean, the same thing. So the action is given here, whatever, d tau, g mu nu, dx mu, d tau, dx nu, d tau. And then we have to use g mu nu for the Kerr metric, and then solve the geodesic equation, and then of course the if you write down this one, so in the lecture note I have written down the expected. So this is equal to, what was that? Anyway, so at theta equal to pi over 2, theta equal to pi over 2, so equatorial plane, so it becomes a bit simpler. I mean, I don't know, it's meaningful to write down everything, but for AM, R and T dot and phi dot, and then plus R square and delta R dot square, and then plus R square plus S square plus 2m S square divided by R and phi dot square. Okay, so that's the action. That's the action, and then I mean. And of course, the one thing, the d lambda is del L del how to say t dot is equal to 0. So equal to 0, which means that this one is constant. So this is the energy, and also the sum not d lambda, d tau, massive case. dd tau del L del phi dot, and this is also the constant. These are constant quantity. Roughly speaking, this is the energy. This is the how to say, angular momentum, and then geodesic is essentially this is equal to -1 in the case of massive particle, and use this constant. Use this constant and just write down what is the variation of the radius direction. Okay. It's last time when I wrote E, epsilon, and L, I think this for epsilon last time I had a typo. No, I think T dot. Last time somehow T dot has some typo. Anyway, so T dot can be written function of the L and E, of course M and A and R, and then what was that? That's function. I don't know. I mean that's how I wrote. Phi dot is phi. T and phi are just function. It's not coordinate. No, it's the same thing. It's L, E, M, A, R. It can be written like this way. If you use this relation, I'm not going to write down the explicit expression. Last time I wrote blackboard, what I wrote blackboard is not correct. There was a typo. And then the important part is the R dot square is 1 over R cube and B tilde, and this also E, L, and R, M on R, and R. Okay, so this is a potential, and then we just need to solve, to consider. So what's important is the circular orbit. So I'm not the expert of this astronomy and so on. But if you consider that for instance, it is believed that all the how to say stationary black hole, real stationary black hole is some kind of Kerr black hole. I mean Kerr black hole, but it's not this eternal one, because the eternal one has again this ring singularity and then so on. That is not real. But we don't know that what's happening in real Kerr black hole inside outer horizon. But it is believed that the stationary black hole in reality is all the Kerr black hole. And this Kerr black hole is so-called accretion disk. If you just do the observation, if you have an accretion disk, and this accretion disk is just somehow black holes just attract many things, whatever, electromagnetic waves and so on. I'm not expert. It's better to ask Cosmo or his student. And then they obey this circular orbit. And so therefore, this circular orbit is the most important object to study in the astronomy. So let's just summarize the result. I'm not going to do the analysis. Because it's horrendous. I just checked the what I have wrote in the Mathematica, but it's not so. I don't want to explain it on Blackboard. Just summarize the results. So B function is written in B tilde is written in the lecture note. I'm not going to write down on Blackboard. It's kind of long lengthy expression, but circular orbit can be just obtained by B tilde is equal to 0 and BR B tilde equal to 0. Okay, so you have to solve this equation. Okay, and if you solve this equation, this one is also, this one I need to write down. E tilde is circular orbit. CO means circular orbit is equal to R square minus 2mr plus minus A squared mr divided by r square root r squared to mr plus minus 2a mr. Okay. And this plus minus means that the one is co-rotating, the other is the counter-rotating. So in Kerr black hole, it's important to distinguish co-rotating circular orbit or counter-rotating circular orbit. They behave differently. Okay? Because as you can easily see from this frame dragging effect, they behave differently. So as you can see here, counter-rotating could become co-rotating inside our sphere, even though the co-rotating become the co-rotating inside our sphere. Okay. So the plus minus is the co-rotating or counter-rotating, and then L tilde of L, circular orbit, is the denominator is the same. Yeah, denominator is same. I'm not gonna write down. Denominator is same, and it's square root mr, and r square plus minus 2a mr plus a square. Okay. Okay, and then you just use just plot the b tilde, and also plot the e tilde and l tilde, and in terms of function m and a and r, and look at what's the, and also if you consider r square b tilde, this is the positive, is it stable, unstable? Maybe I should use this. Stable, unstable. So this is unstable, stable, stable, and so on.
Why? I think that it goes like this, it's stable. The positive second derivative corresponds to a minimum, local minimum.
So that's true, that's true, that's true. This is stable, right? It is unstable, sorry. Okay, sorry, somehow lecture notes is not correct. Yeah, you're right. Yeah. It's positive. Yeah, it should be positive. Okay, good. Okay, so that's how you distinguish. Yeah, distinguish. Okay, and then it's in the case of Schwarzschild, we already knew that the whatever some depending on this L, depending on L and E and so on, the potential become different, right? So if L is big enough, the potential become like this in Schwarzschild case, and there's a stable one, okay, stable circular orbit. But if you change it a little bit, the L is lower, it become like this way. It become like this way, and this is called RMS. This is actually called marginally stable margin. What is it called? Is it? I forgot how to say. MB. Sorry. So this is called marginally bound. Sorry. Marginal bound orbit. Yeah. So this is a marginal bound orbit because I mean here these are bound orbit, but if you just E equal to 0 case, it just goes to infinity. So it's called marginal bound orbit radius. And then in the Schwarzschild case, there is something like I don't remember the detail, but something like this way. And here you will get the it's called innermost stable circular orbit. So this is RMS inner. Okay. Okay, let me write that. Innermost stable circular orbit. ISCO. Okay. This ISCO is believed to be the inner circle of innermost circle of the accretion disk actually. Yeah. Of the Kerr block. In this case, Schwarzschild, but it's important to specify what are those values in the case of the even Kerr. I'm not going to do the detail analysis. The important thing is that also another thing is that the if you take the e goes to infinity, it become the null. Instead of the massive particle, it become massless, a massless particle. That is the case when this denominator vanishes. If this denominator vanishes, e goes to infinity. So when this goes to 0, denominator or maybe I should write down like this way. This goes to 0 when the r is equal to m 1 plus cos 2/3 cos inverse a over m like this way. So if you plug this one into here, this becomes 0. So therefore epsilon goes to infinity. Okay. So in this case, this orbit this circular orbit become null orbit. And then, so that's one of the exercise you have to do in this week, or some of one student already submitted. In the case of Schwarzschild, I mentioned last time. Maybe I should write down like this way. So in the case of Schwarzschild, the massless case also write down a potential. Potential become like this way. In fact, potential become like this way. It is so-called here is called RPH. I call it RPH. This is massless case. Massless particle orbit. So you just do the analysis. You have to do this is the homework. And this RPH in the Schwarzschild, I just give you answer last time. Becomes 3m. So this is called unstable photon circular orbit. Unstable circular orbit. And then one can do the same. So this RPH for Kerr is actually corresponding to this guy, this part. Okay, this part. When this denominator becomes 0, so epsilon goes to 0, so therefore the particle becomes the massless case. Okay. And this RPH is really the position of this unstable circular orbit for massless case. The position here. Once you set a equal to 0, you can replace this RPH equals 3m. It's 3m. And then, yeah. And I just give you the answer of R and B for Kerr is somehow 2m minus plus a plus 2m 1/2 m minus plus a 1/2. Actually, minus is in this case is co-rotating and plus is counter-rotating. And then in the case of the a equal to m, so for co-rotating, this is co-rotating, So for instance, m for m, and then 5.8 m when a is equal to m. A equal to 0, and then a equal to minus m. Okay. So this is Schwarzschild case, and both are extremum. Sorry. It's not co-rotating. I shouldn't say co-rotating. But because once you take a goes to negative, so upper one is counter-rotating, become counter-rotating. So it's okay. So So this R and B is the position of this marginally bound orbit radius. It's called marginally bound orbit radius. Okay, and the marginal stable no, ISCO. The ISCO is in fact given by some complete function which is written in the lecture note. I'm not going to go into the detail. ISCO is in fact m, 6m, 9m, and so on. A is equal to m, A is equal to minus m, A equal to 0, and A equal to minus m. So this can be also obtained. I mean, if you're interested in it, it's a good exercise to do. I think I understand why. Yeah, I think I understand in my lecture note, sorry. In my lecture note, this one is opposite. This is unstable and this is stable in my lecture note. That's because this one. In fact, I mean, in the case of Schwarzschild, I wrote this one is equal to something like a epsilon square minus 1. This is capital E or something. And then minus BR. And then BR. Okay. B tilde. In entire quantity, I just write down this E minus BR. Just in the case of Schwarzschild. Okay. But for Kerr, since B tilde is very complicated, you cannot split E and like L and so on nicely. So therefore, it's just entire object I treated. So therefore, what I wrote is correct. So the unstable sign is opposite. So usually, potential E minus, you just write down E minus B in the case of the equation motion. But we treat everything, so in this case, we treat entire quantity as a B tilde over RQ. So therefore, the sign becomes opposite in this case. Sorry, I think my lecture is correct. So that's the reason.
Why is the condition then on the second derivative of B tilde and not B tilde over R cubed? Since B tilde over R cubed seems to be the, or rather minus B tilde over R cubed seems to be the real effective potential. No? Because at a circular orbit, R dot is equal to 0.
But these are 0, right? Circular orbit. These are 0.
Yeah.
So therefore, even if you act the derivative on this one, the other derivative becomes 0. Do you understand what I mean? The entire quantity, yeah, I agree. So this dr square acts on B tilde R cube. And it depend on sign, you have to decide stable or unstable. But at the circular orbit, this quantity is 0. So therefore, the second derivative only come from, the sign second derivative come from a B tilde part. Both two derivative acts on B tilde part. That's the case. Do you agree? So you have to depends on this one is like this way or the opposite. Sorry. In our case, opposite.
Yeah, okay, I see it. Mm-hmm.
Yeah.
That's true, but this withdrawal of potential, effective potential is not for Kerr blocker, right?
This is not B tilde. This is not B tilde. So this is only Schwarzschild. So since the function of the B tilde is very complicated, it depends on M and A. So if you change M and A and L and E, it's really, I mean, I just play around the mathematics. It's really like, how to say, change a lot. So I'm not going to write down. So it's a horrendous function. So, but still, one can just do the analysis.
And you wrote the energy for ISCO and angular momentum for ISCO radius. This is for, yes, this is for equatorial plane, right?
Yes, equatorial. So here I already set the set equal to pi over 2. Yeah. So if it is not equatorial plane, it's the analysis is horrendous. And there is some mathematical file that analyze the all the geodesic around the Kerr black hole. Not only this equatorial prime. And so those are massive one, and massless one is much more interesting because the analysis is easier and then eliminating. So let's move on to massless. Massless. And then here it becomes 0 now. It becomes 0. And then this is the, okay. And then here, the equation of motion becomes like this way. The r, the lambda, it's not the, since it's massless, I have to use some fine parameter, lambda, instead of proper time. And I call, and this one is equal to r square plus a square minus a square delta divided by r to the fourth, e minus b plus, and e minus b minus. And then here, b plus minus is given by omega plus minus omega square minus g phi phi gtt square root. So omega is actually this is the angular velocity you obtain from the frame dragging, and times L. And this is equal to 2m and r square plus a square minus a square delta L. Okay, so that's the radial part of the equation of motion. Okay, so in order to the so this is somehow the positive quantity outside of the horizon. So therefore, so this part, okay, yeah, this part has to be positive. Okay, since the left hand side is positive and this is positive, so therefore this has to be positive. Okay, so therefore, if you just write down the one second, I don't need to. So if you write down so therefore the region has to be something like this one, for epsilon is still less than b minus. Okay. B minus. And then if you write down b plus and a function as a function, something like this way. So the L is positive, or which means they are co-rotating in my notation. Co-rotating. Then there is a 1. And then something like this way. So this is R0, R plus, okay. And this region is excluded. And this is B plus and B minus. This is epsilon and R. Okay. Since the epsilon has to be greater than or B plus or less than B minus, so this region is excluded. So the mass particle cannot take this region. Okay. So so it has to be something like this one. On the other hand, when it's negative, this is counter-rotating. Counter-rotating, the function becomes the opposite behavior. Something like something like this way. Like this way. This is a B a plus and a B minus, and here you have R. What was that? R plus and R zero, and this is excluded one. Excluded. Okay. Excluded part. And important thing is that here. So, but this is not excluded. This is allowed region. So inside our sphere, somehow epsilon can be negative, energy can be negative. Okay, for counter-rotating massless particle. This is allowed region. Okay, so this is allowed region, and also, of course, so it can be negative. So this is negative energy orbit. So this is a striking phenomenon of the striking phenomenon of the Kerr black hole. Okay. So this is because of GTT can be positive, so that the if you consider the inner product of the full vector of this massless particle and observer, somehow you can have the negative energy. So the rough statement is that so if P is the P mu is the massless, so it's a null vector, and U is observer. If this is the case, U dot P minus is epsilon. Epsilon is 0. Okay, so that's this is the U. U is a full vector for okay. U is the full vector of the observer, and this is massless particle. If there somehow in the the upper light cone and so on include boundary, so this inner product become positive. But if you take the opposite case, P mu and then U mu, if this is the case, minus U dot P can be negative, and then this can be happen in the Argos sphere. This can happen. In Argos sphere, inside Argos sphere. Okay. So because a GTT, so GTT is now is negative, right? GTT is negative inside our sphere. So if you take this somehow the inner product of the del T, it becomes negative. So therefore, somehow this kind of situation will occur. And so this is a very intuitive way of understanding what's happening inside our sphere. But if you try to understand a bit more, one can just do the following analysis. Fine. So consider this U is this ZAMO. MO. So this zero angular momentum observer. So consider zero angular momentum observer. Observer. Somehow spelling is horrible. Observer. Zero angular momentum observer. So in that case, the U mu of ZAMO is given by as follows: UT 0, 0, omega UT. So this is the angular velocity we already derived. The explicit, if you want the explicit value, I can just write down it again. So this omega is equal to 2mr a divided by r square plus s square, and then minus a square delta. Here, everything again. So all the story we talk about is set equal to pi over 2, equatorial plane. Okay, equatorial plane. So here you have sine square theta, but I just put the 1 because set equal to pi over 2. Then, so one can just have the estimate of the P dot U for co-rotating and rotating, counter-rotating and co-rotating. And to do that, here we just need to, okay. So UT, so U is this one. So U dot U is equal to -1. So since it's the observer, so it's just it should be time-like. And then this condition will give you the UT square GTT plus TUT square omega GT omega DT phi plus omega square U T square, and then G phi phi. Okay. So and then you just plug into the this body of the parametric and omega here, and solve for UT. And UT is in fact given by as follows: G phi phi given by GT phi square minus GTT and G phi phi. Okay. Is UT square. UT square is given by like this. Okay. And here, so we consider the future-like, future time-like vector. So therefore, UT has to be greater than 0. Okay. It's a future-like. And now we take the inner product. Yeah. So UT. So therefore, if you take a square root, you only take positive part. So this is equal to square root of this one. Okay. And now we take the inner product with the momentum, massless momentum. Okay. So if you take massless momentum, so epsilon ZAMO. So this is the energy measured by this ZAMO for massless one. Is P dot U ZAMO, and this is equal to something like a minus PT UT minus P phi, and then omega UT. Okay, UT. Okay, so that's the case, and this is equal to minus UT and PT plus omega P phi. And I call it this one is equal to minus epsilon, so therefore this is ut, and then epsilon minus omega L. So this is equal to, in fact, this is equal to epsilon. I define this is epsilon, and this is equal to L. Okay, this is equal to L. Okay. So therefore, so to this one is equal to positive means that the this guy has to be positive. This guy has to be positive. This guy has to be positive. Okay. So what I want to mention is it can be negative. So what I want to show is that it can be negative. But first, if you consider that this epsilon to be positive, this quantity has to be positive. Okay. So this means that the epsilon over L is equal to is greater than omega, and if which is equal to mr. I mean, just omega is the here is the r square plus s square minus s square delta. Okay, so that's what we have, and then. So for massless particle, circular orbit has to be if this epsilon is greater than b plus. Okay, so if it is epsilon greater than b plus, mean that the this one. So b plus is did I erase b plus? Unfortunately, I erased. So if you recall the expression b plus and minus. And plug it into here. Maybe should I write down the unfortunately I erased. Okay, let me write down here. B plus minus is equal to 2mr plus minus r squared delta divided by r squared plus s squared minus s squared delta. Okay, so this is a b plus minus. Okay, and you compare between these two. Compare these two, and okay, compare between these two. And if the co-rotating, object, if co-rotating, this is the case. This is a case, co-rotating, and then epsilon is greater than b plus means that since we have the extra plus r squared delta, right? So if you compare with this angular velocity omega and the p plus, the difference is this plus minus r squared delta. Okay. So the denominator is the same, and the numerator first term is the same. So therefore, difference is this one. So for co-rotating, if the epsilon is greater than b plus, which means that epsilon over L is greater than omega. So this is guaranteed. Okay, guaranteed. Guaranteed, and then am I saying something stupid?
You started with massive particle, right?
Yes.
But why you are talking about massless particle?
No. Here, observer is a massive particle, but this equation motion is everything massless. So, sorry. In addition to that, I have to multiply L. Sorry. That's why I made a mistake. I hope the dimension is okay. Where is it written in my lecture? Yeah, it's correct. So okay, it's okay. So therefore, so this region automatically guarantee epsilon over L is the this one. So therefore, the observed energy is positive. Okay. Do you agree with that? So the answer to your question is that this is dr d lambda square is equal to some factor epsilon minus b plus epsilon minus b minus. So this is the massless geodesic equation. So this is the massless equation. And then since left hand side is positive, this quantity has to be positive. In the case of counter-rotating, this region guarantees that the energy measured by GAMO is positive. That's what I mean. So GAMO, so the P is the massless particle we consider. P is a massless particle. And the U is the observer. And if you take an inner product, one can just obtain the energy of the measured by this DMO. Okay. And then if the massless particle stay in this region, epsilon over L is the, in fact, guarantee that the this GMO, so here GMO, yeah, GMO observer is greater than 0. On the other hand, for counter-rotating part, so for counter-rotating part, maybe I can just write down here. Counter-rotating part, so since the epsilon GAMO is equal to U tau epsilon minus omega L. Okay, and now L is can be negative, right? So it's negative. For counter-rotating, it's negative. Okay, so therefore, even though epsilon is a negative, GAMO can be positive, right? Can be positive. Satisfy. Okay. So epsilon can be, so this can be negative. This can be negative, But still, the energy observed by GMO is positive. If this condition is satisfied, epsilon is omega L. Since right hand side is negative already, because of the co-rotating, so therefore epsilon can be negative. But the measured energy is positive. Measured by GMO is positive. So that's what I meant. Okay, so therefore, in the case of the, and then, yeah. And here, this epsilon is energy measured by the infinity, okay? And this is epsilon GMO is the energy measured by this zero angular momentum observer. And here our focus is GMO inside our sphere. Inside our sphere, epsilon can be negative. So that's one way to justify this is possible. Okay, so therefore the conclusion is that for counter-rotating particle, massless particle, the energy measured by infinity can be negative. Okay, that's the conclusion. And using this, we can just do the following the Gedanken experiment, which is done by Penrose.
Why are we interested in energy observed by Zamo? What is the why we are interested in? You say it should be positive, right? Like,
Yeah.
all the way.
I mean, locally, if you measure the energy, it should be positive, but the energy measured at infinity can be negative. That's what I want to explain. So if you measure the energy inside our sphere, still the observer measure as a positive energy, but at the infinity it can be negative. So in 1969.
So why do, just repeating the same question again, so why do we really care about it? Is it because if we want to write some quantum field theory in that very curved region, if we go through the usual process, we need to identify with the real particles those with this positive energy, and why is this condition so fundamental? That the measured energy
Is positive?
Yes.
Measured energy is positive. I mean,
Where does it come from?
Where does it come from?
I think in the flat space-time, we look
Yeah.
at different, we write some field theory and we look at modes, and
Yeah.
we just call those with positive energy
Yeah.
real particles,
Yeah.
those with negative energy, we call them like,
Negative particle.
well, we call them antiparticles.
Yeah,
like
yeah.
Do some switching around.
Yeah.
And is it the same thing like here? We want to do the same exact process, and this is the quantity that we should be analyzing when we split modes
Yeah,
into
I mean,
particle and particle modes, or what's the...
What's the meaning? I mean, good question. I mean, what's the best good way to answer? But if you believe the equivalence of principle locally, it should be flat, right? It can be flat, right? Equivalent principle. The measured energy at the locally has to be positive, right?
But this has to be.
Yeah.
Comes from where exactly?
Because of the equivalence principle, or principle equivalence. Equivalence of principle, yeah. It has to be locally flat. So that the measured energy has to be positive.
Ah,
Yeah.
okay.
Yeah, locally, inside our sphere. Local observer should measure it as a positive energy. But at infinity, it can be negative. That's what I meant. Okay, but before go to the Penrose process, I think let's take a break. I think okay. So the important thing by definition, the black hole is if you enter it, there's no way to escape. But 1969, the Penrose proposed that the energy can be energy can be extracted from black hole. So so this is called Penrose process for Kerr black hole. And from there, one can just see the glimpse of we can take a glimpse of this black hole thermodynamics. So that's from now on, I'm going to explain, but let's take a break for time being 10 minutes or something. question?
Can I ask?
Yes.
This is the effective potential for Kerr on an equatorial plane.
Okay.
So, and it is possible to extract these things here also.
Oh, you can? Yeah, maybe that's the case. My way of writing is different.
So,
Oh, I think maybe
we can do this as a similar analysis like
Okay.
in Schwarzer, right? So
That's
what
true,
is the
that's
problem
true.
here?
There's no problem. We can do the same analysis. Here you have the parameter m and n and l and the epsilon, right? Also epsilon too. So that's why it's just a bit more complicated. It's the same analysis. Whose book is this?
James Wall, Hartford, James Hartford.
Hartwell.
So it is quite similar to Schwarzschild, for example.
Yeah, you're right.
If you see the Schwarzschild,
Is something with something.
this is the effective potential in Schwarzschild case. This one.
Okay.
And it in Kerr
It's very
case,
similar.
Kerr case is quite similar.
Okay. Okay, I think my lecture notes should be written in harder way in that case. I didn't know that.
Quite similar.
Oh, okay.
So we can do that. These things are this kind of analysis for massive particle as well. So
That's true. But why is it so simple? Okay, maybe if you just somehow massage this expression marked by one of our square, and then extract this part, maybe
Right out the heck.
different. Okay, I'll check this book and then let you know.
and also you are talking about Zamo, right? But
Yeah.
you haven't specified that it is inside the ergosphere. So it is not necessary that Zamo should be inside the ergosphere, right?
No, here. The point is that here epsilon can take the native energy. Yeah. I mean,
In order to observe locally, it has to be like near to each other, like it has to be at the same point.
Yeah.
But where we have specified that it is occurring,
that I agree. But the point is that the only this if you plot the B plus, the only this inside our sphere epsilon can be negative. But so I only like focus on the epsilon goes to B plus region, and then because I mean otherwise this condition is not satisfied and this condition is not satisfied. But if you look at this one, so only the our sphere inside our sphere this epsilon can be negative. That's the point. So therefore, even though epsilon is negative, Zamo inside our sphere can the measured energy can be positive. That's what I mean.
you have specific conditions like epsilon should be greater than V plus, right? In this case.
Yeah.
But if we have this kind of effective potential, what can we do to make analyze this in massive particle case?
Massive particle case?
Yes, you are observing the energy of massless particle,
Yeah.
right? This
I
is-
think it's the same. I think similar thing happened. I think
we don't have this kind of
you will if you include the energy you encounter similar things.
where you get this condition, you V plus, V minus.
So here somehow energy this condition.
But let's assume you have this condition instead of this one. This
Okay.
one. How you impose that V should be positive or negative? Epsilon should be greater than what? There is no V plus, V minus.
Yeah, B plus and minus. So this is massive case, right?
Yes.
Somehow I don't know whether you can write down like this one or this one or not in massive case. I don't know, to be honest. But if you take epsilon goes to very big, it behave like massless, right? Like physically, if you just have even massive particle, if you just take the epsilon, it's very big, so it behave like a massless particle. So this kind of phenomenon should occur. Like if you inside our sphere, epsilon can be negative, even for massive particle.
Yeah, it
It
should be true
it
because
should be true.
Penrose process for massive particles.
Yeah,
right?
also should be possible. So since analysis is easier, so I just focus on massless.
Okay.
Did you make a recording of that lecture that was during the workshop in Hangzhou?
Yeah, I think so. I mean, if you want, I can send a link. I mean,
I checked the YouTube and I think I'm not sure if it was there.
I can show you. To be honest, I don't want to move this one, so can you come here or?
Sure.
Your YouTube channel, video. Yeah, so I think this is the one. Yeah, I think this is the 1 year workshop on
No,
Friday.
this one.
So it's uploaded. Let's get on YouTube. I can send you a link.
No.
Okay.
I saw that. I was just not sure if that was the one. Yeah.
This was recorded, but last lecture 5 is not recorded somehow. Only like 30 minutes or less than 30 minutes are recorded. Okay, let me go to the restroom. And also one thing I want to check is that the Am I correct? Okay, so far so good. Seems so okay. Okay, shall we continue in that case? So let's talk about the Penrose process now. Okay. By the way, yeah, I have to mention. So here, so this part is actually omega r plus L, and also here, this part is omega r plus L. Okay. So omega r plus is an angular velocity for ZMO times L. L is if L is negative, of course this part become negative, and then L is positive, this part become positive, and B plus and B minus coincide at this point. So that's the one thing I wanted to mention. Okay, now let's talk about Penrose process. There are people talking about the Nobel Prize. I personally think Kerr kind of deserves Nobel Prize when I prepared the lectures actually now. But anyway, so that's my personal opinion. But anyway, so Nobel Prize, prize is prize. So. Yeah. So you have the ergosphere and then outer horizon, and then R plus R0, and this is the ergosphere. This part is the ergosphere, and as I mentioned, so So here we talk about this is a rotational black hole, and then you have a counter rotating massless particle just come here, and then so counter particle is dragged to the counter rotating massless particle dragged into the co-rotating. And then suppose you just split into two particles, you just have a nucleus, nuclear waste, and just a flash nuclear waste, and they just escape from our sphere. This kind of process can be done. So this is the observable particle 1, which I call it epsilon 1, and epsilon 2, and epsilon. And this for energy moment conservation, this has to be obeyed. And here, as I mentioned, so this can be negative. This we call it as positive. Inside our sphere, as I mentioned, so this region negative energy is allowed. So suppose we just throw away nuclear waste or whatever you call it. Since we consider it's a massless particle, it should be massless, whatever. But I mean, this process can be applied to even massive one. and then it just throw away something which is negative energy and just move away. This process is possible since at this region, both the thermal of 1 and thermal of the 2, both are positive, measured inside and locally measured in the our sphere is positive. However, the particle 2 has a negative energy at the infinity, measured at the infinity. So therefore, so from here one can just extract the in total energy, since the I mean, how to say, E black hole plus epsilon is the original one, original total energy. This is E total energy, and then E black hole plus E plus epsilon 1. So this guy become E black hole nu eventually, because it's absorbed into the black hole. So therefore, in total, it's this one epsilon black hole nu has to be less than epsilon black hole. So this is the Penrose process. Penrose considered this one. Can you extract entire energy from a black hole? The question is, but this is not the case. So to answer to this question, one can just consider the following thing. So here, not only important part is extract energy, but also angular momentum. So that's the point. So in fact, so this Penrose process is extracting rotational energy. In fact, so in the case of the Schwarzschild, at this point omega r plus is 0. So therefore, in the case of the Schwarzschild, the B plus and the B minus become something like whatever, like this way, most likely, like this way. So therefore, there is no region for negative in the case of Schwarzschild. So once it's extract the rotational energy completely from black hole, you can no longer extract energy from black hole. So there's a limit to extract energy from the black hole. So let us so it's not perpetual process. So it's not. So there is a sense. So it's not a perpetual process, so there is a limit to extract energy. So let us estimate what we are, how to estimate how much you can extract. So to do that, so let's consider the following things. So Killing vector, the vector we consider is the one we consider this one. This phi, whatever, phi. Like this way, if you consider this, this is a future directed time-like vector inside our sphere. But it becomes null, as I mentioned, null at the outer horizon. Okay, outer horizon. And then in falling observer, Oh. Here, it becomes null. So therefore, so this C mu and the P mu, so P2 mu is positive for the since the inside our sphere. So P2 is a momentum for particle 2. So this is a P2 and a P1. This I call it particle 1, anyway, particle 1, particle 2. And if you take a contraction with this vector, so actually this is called Killing vector for Killing vector. I will explain what the Killing vector means in coming lectures, more detail. But I mean, some of the students here already knew that what's the meaning of Killing vector. But anyway, so on Kerr black hole, does not change the metric. Does not change the flow of this vector field is a diffeomorphism of the Kerr spacetime, and then other diffeomorphism, the metric does not change. So that's what the Killing vector means. And then so this is the case. This means that the C mu P2 mu, which is equal to epsilon 2 plus omega 2 J2 has to be 0. Okay. So here, if you take the inner product of the this is equal to what's that? Omega H phi mu. And if you take the inner product with P2, I call it epsilon before, but I just changed to capital E somehow. But anyway, so if you take the inner product, you get the minus energy, and the inner product of phi, you get the J2, angular momentum. I call it this one is the L or something last time, L, but I just changed the notation here. And consequently, so from here, what you mentioned, so this is the change of, this will be change of angular momentum, and this is a change of the energy of the black hole. Energy of the black hole, because I mean P2, the particle 2 enters inside a black hole, okay? So therefore, from here, the change of angular momentum of black hole has to be less than change of mass of black hole divided by omega h. So therefore, the ratio of the change of angular momentum and black hole has to obey this relation. Okay. So this will give you somehow some strong constraints on the black hole mechanism, and which we are going to see. To see the consequence of this change, although it's ad hoc, let us consider so-called area of the outer horizon. It's ad hoc, but let's do that. So this is ad hoc, but let's consider the area of the outer black hole. So area of the outer horizon at r equal to r plus. Okay. So in this case, we just need to consider the metric space metric at r is equal to r plus, which is as follows: gamma ij dxi dxj is equal to r plus s square cos square theta d theta square square and the sine square theta divided by all plus square plus a square cos square theta and d phi square. Okay. So those are induced metric at the outer horizon. And how to measure the area? How to compute area as a physicist? At r is equal to r plus. It's just a square root gamma determinant and then dx, d theta, and d phi. That's what you need to do. Okay. And just take a determinant. Take a determinant. Just multiply these factors and take a square root and integrate over. And what you get is as follows: 4 pi plus r plus square plus a square. So that's the case. And in fact, this quantity, where is it? Oh yeah. This quantity is in fact, if you multiply, the denominator and this one cancel, so what's left is this guy, right? So therefore, this guy is something r plus square plus a square and sine theta. And it just do sine theta integration is super easy, right? So it's a very easy calculation to get the area of the outer horizon. Okay, outer horizon. Fine, and let's normalize. So let's normalize this quantity slightly. So m irreducible. So I call it m. Okay. So m irreducible. Irreducible. Square is the 16 pi. If you want to introduce g, actually there is a g here, hidden g here, and then this one can be written as the 1/4. This quantity r plus square plus a square, and plug r plus value. So this is equal to 1/2 m square plus square root to the fourth minus j squared. Okay, so this is the quantity we consider. And take variation with respect to the angular momentum and the mass. How does, once you change mass and angular momentum, and how does this m irreducible change? Or essentially this area will change. Area will change. So that's a question one can ask. And then a surprising thing happened. I take a variation and then do slightly manipulation. It's a kind of this is not so difficult. You just do the calculation. You just need to do calculation. Take the variation of with respect to mass, and then be careful about the notation of the omega h. Did I write the omega h at some point? Yeah, I wrote, right? I already forgot something like r plus square plus a square. Yeah. So this omega. Did I write omega h? So this is omega h, and this quantity is equal to. I just remind you, this is equal to a r plus square plus a square. This is the angular velocity at the outer horizon. Okay, outer horizon.
Here, once again, m irreducible is just some quantity that we define. It's not.
We define.
Yeah, it's not supposed to be anything meaningful right now.
Not meaningful right now. Yeah, you're right. Okay, so and take variation. How does it behave M irreducible with respect to variation of mass and J? Okay, and you will get this one. But since from Penrose process we obtain this quantity, okay, this inequality. So therefore, this has to be positive. Okay, this has to be positive. So therefore, M irreducible. The reason why it's called irreducible mass, it's called irreducible mass, but it cannot be. It never decreases. Therefore, it's called irreducible. Okay. If you define this quantity for Kerr black hole, this quantity never decreases. That's what it means. So therefore, so this means that the area of outer horizon A never decrease. Okay, so that's the immediate consequence of the analysis of Penrose process. Even though you can extract energy from somehow, if you extract energy from black hole, you may think the black hole may shrink, but that's not the case. That's not the case. There's something Kerr black hole. Since you also extracted the angular momentum, so therefore area has to increase instead of decrease. That's a remarkable consequence. Remarkable consequence of the analysis of Penrose process. So therefore, since you extract the energy in addition to that, you also extract the angular momentum, and the R plus is the M plus square root M square minus S square, right? Square is equal. Sorry, correct me if I'm wrong. I just want to check. It should be okay, right? Am I wrong? Yeah, it should be okay, right? So if you change M, also if you change A is the related to J. So therefore, the area can never decrease. Can increase. And in fact, it has to increase. Or never decrease. So this, okay? And somehow this is somehow related to first law of thermodynamics. Delta S is always like this way. Entropy never decreases. So it's a very similar statement of the thermodynamics of the first law. Okay. So we can do a bit more manipulation. Sorry, not first law, second law. Sorry. Second law. Second law of the thermodynamics. And then you can just do this a bit more. So the reason why it's called irreducible is that it never decreases. That's why it's. And in fact, the energy that can extracted from the black hole is always this one. The maximum energy which can extract from the black hole is in this quantity. Yeah. Oh, where did I write the definition? Okay, so yeah. So if you take a square root, so m irrad is equal to square root 2 m square plus square root m4 minus j square 1/2. Okay. So this is the case. Okay. So in the case of the Schwarzschild, j equal to 0. Okay. So therefore, this is 2 times m square, and the square root 2 is the square root 2 cancel. It becomes mass of the Schwarzschild. So from Schwarzschild, you cannot extract by the Penrose process. That's what you mean. But the maximum energy one can extract for Kerr case is this quantity. This quantity. Anyway, So, and also if you do a bit more manipulation on this, maybe down here around here. So if you just do the delta A, so if you do the computation of delta A, this will become, it's very easy using this relation. Using this relation, delta A can be written as like follows: 8 pi A. Maybe I should write down like this way: 8 pi A over omega H square root m square minus A square delta M minus omega H delta J. That's like how area will behave under the exchange variation with respect to mass and angular momentum. And I define this quantity. So I call it this quantity as the 1 over kappa. 1 over kappa. Just the definition. And then, so this law can be written delta M is kappa over 8 pi del A plus omega H delta J. Okay, delta J. And so that's how the variation of the area, mass, and angular momentum for black hole. And somehow people call this kappa is the surface gravity. Surface gravity. Surface gravity. Okay. And then somehow this really resemble, resonate with the dE is equal to TdS minus plus minus P dB. So this is the first law. This is the first law of the thermodynamics. Again, the area plays a role of the entropy, and the mass and energy. The analogy is straightforward. And then the temperature and then somehow surface gravity is the in a correspondence. And the other quantity as well. Okay, so this is the somehow if you consider the Penrose process, somehow naturally this the analogy to the black hole thermodynamics will appear. So this is kind of magical. And in fact, area never decreases, so delta A. So this is the one of the specific example called the Hawking area theorem. So this is the Hawking area theorem. Is the yes. And we will okay. So that's the one way to motivate why we need to think the black hole thermodynamics. Somehow, if you consider a black hole and consider Penrose process, this somehow analogy naturally appears in the end, at the end. Any question at this moment? Okay.
So we are showing that the area cannot be decreased by Penrose process, right?
Yes.
But is there any processes or ways to decrease the area?
So that's the point. So this analysis is only coming from the analysis of Penrose process. But so Hawking theorem means that there is no process that can decrease the area of the black hole.
But we haven't proved it yet, right?
We haven't proved it yet. So this is a specific example of, in fact, it's just that hindsight. So this is a specific example of Hawking area theorem. But to prove the Hawking area theorem, I have to introduce a lot of things, like a Ray-Chandler equation and so on. So you have to wait. Any question at this moment? So it's a specific example of the area there. Good. Fine. So those are the. My plan is that okay. How many people already know Friedman? I have to mention that it's not the Lemaitre. Okay. So I have to. So. I just in this lecture note, I just give kind of anecdotes of the physicists or physicists who also make a great contribution. So people just mentioned that the Friedman, Robertson, I need Robertson, Walker. Metric and so on, but here we have to include so-called Lemaitre. He's Belgium. I don't know. It's a French name, French pronunciation. I don't know how to pronounce Lemaitre or something like that. Lemaitre. Actually, Friedman is the paper is up here 22 or 24. His paper 27 and 31, 30 to 34 or something. So we have to include Lemaitre. He's a very modest guy. Actually, I included the comment, include anecdote, but Hubble constant, people call it Hubble constant, is actually first introduced by Lemaitre. Anyway, so in my lecture, I call it FLRW metric. How many of you learn about the FLRW metric? Okay, about 60 or 70%? Okay, 60 or 70%, something like that. Maybe, and then, but I just want to talk about the dosita and the anti-dosita at least, of structure of anti-dosita. So again, repetition of father of learning. So let's talk about a little bit about the exact solution of the cosmological exact solution. So, okay. So most of you guys already learned FLW metric, and then DS and ADS. That's I'm going to talk about. So these are cosmological exact solution to the Einstein equation. So, yeah. So far we learned that the black hole, the Schwarzschild, and then Reisner, Longstone, and the Kerr, and then potentially in the homework you have to check Newman. So those are exact solution as a black hole, but for cosmological, exact solution also plays important role. Anyway, so this actually Lemaitre is the first person who proposed so-called Big Bang theory. Anyway, so this FLRW somehow knows about the history of the universe, and DS is actually our describe our universe at this moment, and that anti-dosita is also plays a very important role. As you might have heard of it, is CFT correspondence and so on. So it's better to learn this kind of stuff. I don't think people just does anybody is any course explain the dosita and anti-dosita? No, right? No, not at school. So I think it's better to explain. Okay. Anyway, so today is lecture 6, right? And I think presumably we have 13 or 14 lectures, so still we have plenty of time. And I mentioned that I just do it slowly in this course, so it's okay to do some review of the Riemann-Robertson-Walker metric, Lemaitre-Robertson-Walker. Freeman is actually this yeah, probably he knows. He's from the Soviet Union. Actually, after he wrote a paper on this whatever homogeneous isotropic universe, 25th he died. Lemaitre actually in 27 he wrote a paper on this the expanding universe, and then he introduced a notion called Hubble constant already 2 years before Hubble. And then Robertson Walker is actually dynamical homogeneous isotropic universe. So that's the history. Okay, so let's talk about the homogeneous and then isotropic universe. Okay, so homogeneous isotropic universe, we assume that the following form. So the metric is kind of this kind of form, Gij. So this is the three-dimensional metric, dxj, which takes the following form: a square and dr square. Sigma ab. So like this way. Okay. So and here you can just replace it by constant, and the Riemannian tensor. So this is homogeneous isotropic, means that the Riemannian tensor JKL number 3. So this can be replaced by d omega 2 squared actually. So that's the case. And the homogeneous isotropic means that it takes the following form: GIK number 3. So this is ansatz. GAIL number 3 minus 3 GIL 3 GJK. Okay. So if you just consider the following metric, the Riemannian tensor takes this kind of form. This is called homogeneous and isotropic. Okay. And if you define a new coordinate, something like r is equal to minus k, and then sinh square root minus k and chi, then A takes the point. The metric can be written as follows. So this metric can be written as follows. Depending on the sign of k, you have the d chi square plus sine square chi d omega 2 square, and then a square d chi square plus chi square d omega 2 square, So this is k is equal to essentially 1, k equal to 0, and k equal to minus. And this is a square, d chi square plus sinh chi d omega 2 square. Okay. And this is called a flat. And this is called a sphere or a 3-sphere. It's a metric of 3-sphere. 3-sphere. And this is called hyperbolic. Or H3. Hyperbolic. And then, of course, the curvature is here. Curvature is positive or negative? Positive, and 0 and negative. So that's the case. And then, so what we are considering is that the the total metric is something like this one. So this minus, I don't know why I just increase dx0 squared plus a t x0 and then gamma ij dxi dxj. So that's our assumption. Here now, so this guy can depend on time, or maybe t is okay. I already ignored c and so on. So like this way, can depend on time. Time t. And here, this can be understood as size of universe. Size of universe. So because it plays a role of the whatever, the radius or whatever, R's radius of the.
And what you call gamma now used to be G3.
Gamma is the sorry, you're right. Somehow my notation is French. Thank you very much. Yeah, you're right. G3. I don't know why I call it gamma. G3. Yeah, thank you very much. Like this way? Yeah, you're right. Yes, fine. Except this part, a square. A square is now like a depend, just extracted, and then it depends on time. I think the way I wrote is not correct. It's not good form. It's not good form. Okay. And it's, we need to solve the Einstein equation. But here we assume that it's not vacuum, so it's kind of like it's perfect fluid. So universe is filled. So universe is filled with the perfect fluid. So therefore, T mu nu is equal to rho u nu plus p g mu nu. And where u is given by how to say, u is t a. Okay, like this way. Maybe I should call small t or whatever you call it. And then this is the energy density, and this is the pressure. And locally it can be written like this way. Okay, locally, if it is flat, and then locally. So this is a definition of perfect fluid. And it just we need to solve. We need to solve the. Sorry, that I think I made that mistake. I made a mistake. So this is the plus u nu. Okay, I think that's what we need to. Yeah, I think this is the case. Sorry. So this is the case. And then we just need to solve the Einstein equation, where I assume still keep the number. We just need to solve the Einstein equation, and let's do one by one. Okay. So Einstein equation, I just wrote down the so the R mu nu minus 1/2 G mu nu R, and then I include the cosmological constant in the right hand side somehow, pi G. I don't like a G, so I already declare the G and C equal to 1 T mu nu minus lambda G mu nu. And then we just need to solve the equation, and then just being brief. Where's the? And I call it this one is capital G mu nu. Capital G mu nu. I just need to be brief. G00 can be written as follows: 3 times a dot. Dot means the time derivative, and a square plus k divided by a square. So that's the G00 component. Just plug this metric. Plug this metric into here, and then you will get this one. So that the important thing is that although like a complicated, it's not complicated. It's just in the case of homogeneous and isotropic case, what's important is this factor of k and the a. Okay. And the Gij part can be written as follows: 2 a dot over a plus 3 a dot a and square plus a k. C. No, I don't like C. I don't know why. C square and 3 Gij. So it's proportional to Gij. So this is one of the consequence of a homogeneous case, and then just you equate the T mu nu. And T mu equal to T mu nu minus the metric. The first equation is from the, so therefore from first equation one can obtain as follows. So right hand side is equal to, so if you look at this T mu nu, maybe the T mu nu, so the first components come from rho. So therefore right hand side is something like 8 pi over 3 rho, and then plus lambda divided by 3. Sorry, no need to 3. No need for 3. I think it's just coming from 8 pi rho plus lambda. That's That's the case. And then here you have the point. The right hand side is minus 8 pi p plus lambda. Minus lambda. Okay, so that's the case. And then if you substitute this guy, so you can just substitute this guy into here, right? Into here, and then just eliminate this part. Then one will obtain the following. What's going to happen? Is it okay? I think I'm doing something stupid. I think I'm doing something stupid. Sorry. Is there some mistake in my calculation? In the lecture note?
The signs are zero. The signs are weird because lambda has a G in front of it. So the
Yeah.
zero component should have like
Yeah, you're right. You're right. You're right.
minus lambda.
You're right. The sign's strange. You're right.
And the GIG, the right hand side should have a delta IG.
Yeah, this is a minus actually. And then yes, and this is should be minus, but still somehow was somewhat strange. Where did I make a mistake? You are right. Let me think. Okay, somewhat strange. So the first equation is okay. The second equation I wrote does not consistent with my lecture note. That's not good. But somehow that's how it is. I made a mistake somewhere. Anyway, so eventually, I think I will correct the lecture note later. So what you get is that if you take the somehow the second equation becomes something like this way. In my lecture note, is it correct? And now like kind of like a downing. But it should be okay. This should be okay. K over S squared is equal to minus 4 pi P plus lambda. Does any students find a mistake in my lecture note? Or it's okay? I don't know where I made a mistake, to be honest. Maybe
So what happened to row?
I don't know, to be honest. Where did I make a mistake?
I think it's possible to get like two equations, one relating P and row,
Mm-hmm.
and another one with just row or just P.
Okay, I will check my calculation later. Let's accept these two equations somehow. These two equations, then what you get is as follows. So A double dot, so A is equal to minus 4 pi over 3 and rho plus 3p plus lambda divided by 3. Okay. So that's the equation you obtain. That should be okay, right? If you divide it by this one, this should be okay, right? Yeah, this should be. So plug this guy into here, this you have the 8 pi rho divided by 3 plus lambda over 3. And then bring to the here. Somehow, even power of lambda is somewhat strange. Did I make a mistake? Can anybody find some mistake?
Why is the power of lambda strange? Your notes just have the power of c.
You're right. This is equal actually 2 divided by 2. Okay. Divided by 2. Then, but still somehow powers look strange to me. What's going on? Sorry.
Well, in GIJ, it looks like you substitute on the right hand side. You substituted just a flat metric because you have minus lambda. But it should be minus lambda A of t GIJ. So, and after we kind of divide, maybe then we'll get something.
Okay. True. Can anybody find my mistake? Okay, I think let's assume this one. Okay, I will try to correct my lecture note later. So let's assume this one. Let's assume this one. So this is called this is called Friedman equation. Okay, if lambda, so the important thing is that if lambda is equal to 0, if lambda equal to 0, so this quantity is negative. So rho and p are positive quantity. So therefore, right hand side is right hand side is the negative. So therefore, so the A dot has to be negative, which means the decelerating, and that was deceleration. Okay. So therefore, however, so in our universe actually, so are we accelerating or decelerating? Accelerating. So therefore, lambda has to be positive. So that in our universe, the accelerating. So observation means the observation of the. It was supernova 1998, right? As far as I remember. So it's accelerating universe means that the lambda should be positive. Okay, so that's the case. Okay, and now we can just focus. So far we just solved the Einstein equation, but now we just consider the equation of motion. So equation of motion, since the equation of motion is del mu t mu nu is equal to 0, is equal to del mu g mu nu is equal to 0. So therefore, we just apply this with respect to time, and then using. Okay, so we just apply. So this is a time derivative, apply time derivative. So, and then we just use this equation and to obtain this, the following, the law of the conservation. So rho dot plus 3 A dot over A, rho plus P equal to 0. Okay. So this is equivalent to the so this is equivalent to the this guy. Okay, so this is this guy. So this is a law of conservation. Conservation. Okay, so then one can just obtain that when combined with the state equation, P is equal to P rho. So if you have a state equation, one can solve the equation. Equation of state is called equation of state of state. If you specify equation of state, so we have P and rho, and this equation, and then this equation, we have a 3 equation for unknown A and rho and P. So you have a 3 unknown variables, 3 equation, one can solve the equation. Okay. And to solve that one, so one just assumes that the pressure can be neglected. So, and then rho is somehow constant. Okay. So if P is a pressure, so you can easily see if you go to the university, there's no pressure. Right? I mean, you don't need to take an exam. You don't need to worry about life, so you don't have a pressure. So that the so we can set the P equal to 0. Pressure can be neglected. So therefore, we plug it into this one. So therefore, rho dot plus 3 A dot A E times rho equal to 0. So from here, you have a 3 A dot over A is equal to minus rho dot over rho. Okay, and from here, rho is equal to rho 0 over A to the cube. Okay, so that's the behavior. Okay, and then plug that one into here. Which equation is the best? To there. Then what you get is as follows. If you plug this equation to here, if you plug this in equation, so A dot over A square plus K over A square is equal to 8 pi. So 8 pi, rho is this one, right? Rho 0 over A cube plus lambda. Okay, that's what you get from here. And then you just do the manipulation. You just multiply some factor, and then if you massage this equation, what you get is as follows: 1/2 A dot square plus B of A is equal to minus 1/2 K times minus K, where this guy, sorry. I didn't get to the point, sorry. This is equal to minus 4 pi G divided by 3 rho 0 over A minus lambda of 6 A squared. Okay, so that's what's happening here. And then we will see, okay, maybe it's running out of time, so we just consider that some cases. So this potential becomes if you choose some appropriate lambda, it becomes like this way. So K is equal to 1, it's like this way, K equal to 0. And K is called minus 1, it becomes like this way, and so on. And this is called Einstein, the unstable form Einstein static universe. Which I think I will recap this next time. This is K equal to minus 1, and so on. I think opposite, sorry, plus 1 and a minus 1. Because so if you plug K minus 1 into here, this minus sign, it becomes positive, and so on. And that's what's going to happen once you choose lambda equal to 0 and so on. Okay. Appropriate lambda. Okay, appropriate lambda. So that's what I will recap next time, but let's stop here today. Yeah, sorry about the derivation. Somehow I missed.